here, live coding again on RaptorJIT, and the topic today is again the sealed tables optimization. This is a new optimization that we're putting into RaptorJIT to allow the compiler to do a little bit more work at recording time and not at runtime, to speed things up and provide redundancy to some other optimizations. So before what we want to do today, really the high level goal is to take a first step towards implementing the barrier that will detect when our machine code is invalidated and needs to be regenerated. So the thing with the sealed tables is that we have certain tables. We tell the compiler that these are sealed, and it should inline the values it finds in those tables directly into the machine code. And this depends on the invariant that machine code is always up to date with respect to the contents of the tables. If the content of the tables changes, machine code needs to be invalidated so that it can be recompiled by the JIT. And that's not implemented yet, and we need to find the right places in the source code where we detect when a table write needs to invalidate the code. And in order to take this next step, there's actually a bit of relevant background context that I just want to brain dump out. This is things that have been thrashed out on the GitHub repository in issues over the past half a year or so, and it explains a little bit about the character of RaptorJIT and the ways in which it diverges from the LuaJIT strategy in certain ways. So I'm going to do a bit of a brain dump on some things there, and I wrote down a little list so that we don't get lost. This is our stack. We're going to talk about compiler bootstrapping a little bit, the RaptorJIT approach there, how it differs from LuaJIT. We're going to talk about the merits of assembler-vs-C for the virtual machine. We're going to have a little bit of a look at how the LuaJIT Bytecode Interpreter is written, and say a little bit about why I'm interested in taking a different approach for RaptorJIT. That leads directly onto another feature that we're going to hack on another time in the future that has a dependency here, which is the 96-bit VM, which is something I'm very excited about. I think it's going to be a killer feature. It remains to be seen, but I'm very excited about that. But we need to sort out a couple of dependencies before we can do that. And finally, then we hope to come back and actually look at survey the code that is going to be impacted by the table sealing table write barrier. And just come up, get it straight in our heads, which files and functions we're going to have to update to make that work. So let's do this. So for the first item, the way that this came into my mind was that after the last live coding session, we got a testable version of the sealed tables feature, and I put that on a branch, and I made a pull request out of that to the RaptorJIT repository, flagged as being an early version, with to-do work to do. So I always like to do this. If I have an idea or a rough draft, anything that I would like to get put on other people's radar, I always like to do a pull request somewhere so that it's out there. There's a comments field that people can say things. People can. It's quite nice. People can even just come and leave these kind of like, hooray, I like that. For me, this is valuable. You can test the water a little bit. Someone might see a crucial fault and point it out and save me a lot of dead-end work or whatever. I like the social side of this kind of development, to get stuff out there and in front of people and exposed to feedback. And in addition to being exposed to feedback, it also exposes it to continuous integration. So when I posted this, it got a fail from the CI, which is running on Travis. And the reason for this failure is what leads us to the compiler bootstrapping issue. So if we go out to the continuous integration server and ask for the details of this error, it's gonna, well, we look at the configuration for this CI job. It runs on some version of Ubuntu. I don't know which one, and I don't care. It uses Nix to pull in all the dependencies, so we're not using the compiler, the libc, anything from this random Ubuntu. Everything is kind of using a pinned version of everything, so the test is reproducible on any host. And it just runs the normal test suite with the JIT turned off, with the JIT at optimization level 1, 2, and 3. It runs the test suite with each of those settings. And then it also runs this check-generated code. And that's what is failing in this case. So if we come over to the log, and we scroll down, the error we got is this. The CI has detected that we added a new primitive function called jit.seal, and we didn't do everything that's needed in order to land that change on the master branch. And this is an interesting thing. So the VM generates some code. How should I say this? When you build the RaptorJIT VM and the LuaJIT VM, some code is generated during the build process for the VM, and that code is generated by programs written in Lua. And this is a bootstrapping issue, right? In principle, you kind of like, which version of Lua do you use for building the Lua compiler? If you would say that we use our own version, then you have a circular dependency, because you can't build your own compiler without using your own compiler to do it. So somehow you need to break this circular dependency, and LuaJIT does it in one way, and RaptorJIT does it in another way. So the way that RaptorJIT does it is really in two ways. The simplest way is we just say, give us a LuaJIT to bootstrap from. Like, whatever. It's not a huge practical barrier actually to go off and get a version of LuaJIT, at least if you're doing development on RaptorJIT. If you're actually hacking RaptorJIT and maintaining RaptorJIT, it's not a big imposition to have some random version of LuaJIT that can just do the bootstrapping for you. Or it could also be another version of RaptorJIT, whatever. Just say, give us a Lua system to bootstrap with. But that's a pain from a user perspective. If you're a user, if you're embedding RaptorJIT in another application, you don't really want to need to have this, you don't want to add LuaJIT or another Lua system as a dependency there. So the compromise we've made at this point is to actually check in the necessary generated code into the repository. And this is like good and bad, right? The good thing about having the code checked in is then you don't have to do the bootstrapping. You can just do this. Hold on, I'll show you that. So when you build RaptorJIT, you actually have two options about the way you want to do it. You can just say make, in which case it expects you to have a LuaJIT available for it to run its bootstrapping, or you can say make reuse VM, in which case it's going to just take all the generated code out of the that's already checked into the repository and just build that instead of regenerating it. So in that case, you don't need any Lua system to build the compiler, because the generated code has been pre-generated and included in the source tree. And obviously, this creates a nasty problem, right? Like, how do you keep the code up to date? If you have generated code checked in the repository, you're creating a kind of a synchronization problem. And the way that I'm dealing with this in RaptorJIT is to use continuous integration, to say the invariant that we want to make users happy is that any version of RaptorJIT that you would pull from the master branch, like a release, has to have perfectly up-to-date generated code. So if you're pulling from the master branch, you're using releases, you should always be able to trust that the code is fine. And that's exactly what the CI is testing here. So this CI test is generating all of the code from scratch and then diffing that with the code that's in the repository. And what this here is saying is that when it did the diff, it detected that when it regenerates the code, it has this new primitive function that isn't there in the code in the repository. So what that means is that CI is not going to accept this change until we regenerate and update the code. And we don't have to do that right now. That's only something that needs to be done in order to land the code in a release on the master branch, because the invariant that we want is that if you're working on the master branch, the generated code is up to date and you don't need a Lua compiler for bootstrapping. If you're working on some random development branch like this, then the expectation is that you will use be bootstrapping the VM using some other Lua, another version of RaptorJIT or LuaJIT or whatever. So that's the expectation. So that's how we're dealing with this problem in RaptorJIT. In principle, the build does require an existing Lua compiler in order to bootstrap itself, because it needs to generate some code with Lua. But in practice, if you're going from the kind of the release branches, then you can skip that step if you want to. It's no problem, and the CI makes sure that it doesn't blow you up. So what we see here is just the CI doing its job, and I would kind of tend to worry about this last. So this is something that needs to be resolved before this change merges to master. But for the moment, it's not a big deal, because I can still work with this just doing the normal build with a Lua compiler. So that's the current RaptorJIT approach, and I don't think it's perfect, and I would like to improve it in the future. But it is it has allowed. Well, I've got a bigger problem with the way LuaJIT does things. Is the thing. So now we'll look at the way LuaJIT does things, and that is a lot more a lot more clever, and that's a big thing. RaptorJIT is not supposed to be clever in things like the way the VM is built. I want to use you only have so much brain capacity for doing clever things, and I want to reserve that for the applications I'm building. I don't want to burn all my kind of creative cleverness on things like building the compiler. For me, building the compiler is one of the most boring things in the entire kind of universe, even though I know that bootstrapping compilers for many people is a passion. For many people it's very exciting, and people are very motivated to do a lot of work there. For me, this is the thing I just want to work. Anyway, I digress. I digress from my digression. Let's look now at the way LuaJIT does things instead, just to give the flavor. So LuaJIT has a very nice property, and by the way, Peter Corley has done a very good talk on this topic on the LuaJIT side, and that's partly what triggered the RaptorJIT thing. For me, it was a bit of a tragedy that you get some very, very, very brilliant person like Peter Corley up to do a talk, and for me, it gives me pain in the heart. It feels like a wasted opportunity when what they talk about is how to build the VM, because for me, there are 100 other things I would like to have heard him explain and talk about, so I feel like it is a damaging distraction that it's so much work to just understand how the VM builds. Anyway, the way LuaJIT builds this, the way LuaJIT does the bootstrapping is very clever and very, very practical as well from a user perspective. So what they do is they create a new, basically they make a new implementation of Lua that is a single C source file that you can build with no dependencies, that is only used for doing this code generation during boot. So it's like a little fork of the Puck Lua from Brazil. It's a little fork of that that's only used during build to generate the code. So they've got a whole like Lua implementation just for bootstrapping, which is, my hat is off, right? That's hardcore. Let's look at the code for that. If we go into the LuaJIT repository in the host, we have a file called minilua.c. And the comment says, this is a heavily customized and minimized copy of Lua 5.1.5. So somehow they've started with Lua from Brazil from 2012, and they've just stripped it down. And this is something that's been stripped down by hand, as I understand it. It's maintained by hand, as I understand it. It goes down, it's a C source file. There's no indentation, there's no blank lines. If we just page down a bit, like it's just code that you just wouldn't want to have to maintain. So I think the idea here is you do this once, and then you just try to never, ever, ever touch this again, or absolutely as little as possible, right? So this is a very, very, very special purpose, unmaintainable version of Lua. It probably has very little error reportage, anything like that, but it gets your bootstrapping done. And you know, the pain, I guess Mike Paul did this and he already took the pain hit of this, and now if you just pretend it's not there, it doesn't matter. You don't have to care about it. That's the way I think it is. I hate this. I hate this. Like this is 7,500 lines of obfuscated C code that's being maintained by hand, just you know, as part of the bootstrapping story for the compiler. So I realize that a lot of people probably see this and think that is the coolest thing I've ever seen, and my visceral reaction is just the opposite. I don't like this. So I deleted this file from RaptorJIT. I mean, I've deleted about half the LuaJIT source code so far, and I want to make it all as small as I can, and I got great satisfaction from getting rid of this, because I don't want to understand this code. I don't want to make changes to this. I don't want to find that I get obscure error messages that I don't understand while dealing with the code generators, and then have to trace those back into this file to understand what's going on, and maybe find, you know, that some of the error handling was stripped out. Or for me, this is like zero interest in this code. Anyway, I guess I've made my rant there, and I realize not everyone will agree with me. But for me, this is hard to maintain. I want things to be easy to maintain, and that's why I've taken a different approach here. That's all I wanted to say on the topic of the reuse VM idea. So the next thing is a little bit related. It's the bytecode interpreter. So the reason that this is relevant is for the sealed tables optimization, we're going to need to make sure that every time a table is updated, every time the value in a table changes, we check this barrier. We see, was that a sealed table? If it was a sealed table, then invalidate machine code. So we need to go through the VM, both in the just-in-time compiler where it generates code for updating tables, and also in the interpreter when it just when it interprets bytecodes that are doing table updates. We need to update both of those to enforce this this barrier that we haven't quite thought through yet, and that's the big topic. And this is the first time on the live coding that this leads us into the bytecode interpreter, which is also an area where I have a very, very different idea for how I want to do this compared with LuaJIT. And I think I'm just going to open up the code a bit to explain the LuaJIT approach here. So you might recall that in sealed tables we already opened a file called ljrecord.c, and we looked for the bytecode like tget. We looked for the way that we compile the bytecodes for table lookups, and we have table writes as well down here. Tset. So we looked for this, where is the implementation of this bytecode tset, and what we found was that basically everything for all of the various bytecodes, basically everything is done in this helper function called ljrecord index lookup, which is great, and it turned out to be really simple. I'm still kind of shocked at how straightforwardly that this optimization has gone up until now, if we don't find any crucial problems. So that is great, and now this is for reading from sealed tables. Now when we come around to writing to sealed tables, then we need to repeat the exercise. Where is the implementation of writing to sealed tables? And in this case, we care about the interpreter as well. So on the reads, we didn't care about the interpreter because the interpreter doesn't do anything special for reads from sealed tables. It's only the JIT compiler that does. So we go now into the virtual machine. So this is the LuaJIT source tree. We have a few files for the virtual machine. There are actually 1, 2, 3, 4, 5, 6, 7 separate implementations of the virtual machine. I pull up one. The x64 is the one that we care most about. So each of these implementations is an assembly language program. That it's for me it's kind of like, it looks like a fourth interpreter, more or less. That's kind of the flavor here. If you read Jones fourth or something like that, it's a pretty similar kind of a program to that. And of course this code is written using the x86-64 instruction set, so it's very specific to that platform. And LuaJIT supports quite a few platforms. So if we just do a little word count, we have all of these implementations that they all do exactly the same thing. It's actually kind of a requirement that they all do exactly the same thing, because these are ports, right? They all need to be equivalent, but they're all written from scratch. So we have 4,000 lines of code for ARM64, 4,500 for ARM32, 5,000 for MIPS64, 5,500 for MIPS32, 6,000 for PowerPC, 5,000 for x86-64, and nearly 6,000 for x86 32-bit. And actually, and that's, I mean, if you're going to be maintaining this, you need to be a special kind of a person, right? You need to be somebody who is comfortable with maintaining all of these in parallel and keeping them perfectly synchronized. I would think you also need to have a lot of kind of test infrastructure, at least based on QEMU or something like that. You want a way to run the test suite for all of these platforms so that you can verify. Because if we make a change, we're running on this platform here, but if we update this VM, then in principle we also need to make an exactly equivalent update to all of these other ones. And I don't have like a MIPS box handy, for example. And it's not just the CPU architectures either. There's a lot more variables inside here, like there's platform support, there's Windows support, there's Xbox support, and so it's kind of a lot of different factors. And there's more factors than that too, like the way it's very impressive. The thing here is that this is very clever and very impressive and very kind of amazing that people can do this. I'm in awe. So like with this 64-bit VM, for example, even within there, it's very if-deft, because you actually have both a version where you see 64. You have a version where oh, sorry, I'm thinking of the x86. Am I? You can run the heap. There's two kind of related questions. Do you use 64-bit instructions and 64-bit registers? That's the x64 versus x86. And the other question is, do you use 32-bit or 64-bit pointers into the Lua heap? So there is a mode where you do use the 64-bit registers, but you squish the Lua heap into like a couple of gigabytes of address space, so that you can make your pointers be just 32 bits, so you have more compact pointers. So keeping all that stuff also kind of perfectly in sync when it's got kind of very big implications. You know, that changes the whole heap layout. It's very intricate. So it's very, very intricate. I don't know. I don't want this situation. I don't like this. I want, here's a case where we've got an optimization we want to do. The sealed tables, it looks very valuable. We just want to get it done, and the interpreter here is basically just an obstacle, because we're not actually getting any benefit from the interpreter being hand optimized in assembler. We're paying a big price that every time we want to do an interesting change to the VM, we need to go into 7 different architectures and make, you know, perfectly balanced changes to them. That's a huge cost for me. For me, this is almost going to drown out, you know, people doing, you know, 9 out of 10 or 99 out of 100 people are not going to be willing to make even small changes to the VM when that's the cost, when you need to do it like that. That's what I think anyway. It bothers me tremendously. It's a huge barrier to doing anything interesting, having to deal with all this assembler code. Sorry, I've ranted myself all the way off my stack. So what I want to do in RaptorJIT is actually to just rewrite this in C. Yeah, so I was saying that we don't get any benefit from having this all hand optimized. So yes, the interpreter is faster. At least it was when this approach was taken like 10 years ago or something. There is a famous email somewhere with a benchmark showing that the assembler code beats the C compiler, and this was all very clever, and it's been a bit of a part of the mythology of LuaJIT that the VM is written in assembler, and as a demonstration of Mike Paul's amazing programming capabilities, that he can kick the C compiler's ass, right? That's been a part of the LuaJIT brand, and that's very cool and everything. But I want to make things maintainable. I feel like the complexity of the interpreter is a huge barrier to doing really much more important optimizations, because I don't care to a first approximation how fast the interpreter runs, because in my experience doing like 6 years or something of LuaJIT hacking in anger on applications, you just can't use the interpreter in performance-sensitive code. If you're performance-sensitive, if any significant part of your workload is falling out of the JIT and onto the interpreter, you're hosed. That's my experience. So I see the interpreter as something that you use during warm-up, before you've taken the JIT for a run, and that you use for really obscure kind of code paths. Maybe for, you might do some first configuration changes. That's fine to take those with the interpreters. You get an unexpected, unusual exception somewhere, the interpreter handles that. It's like a safety net. But I would never ever put any performance-sensitive code on the interpreter. The first step of any kind of serious application optimization effort is to make sure nothing runs on the interpreter. And once you've already kind of decided that in your head, it wouldn't matter that much. If the interpreter ran 10% slower, or 20% slower, or 50% slower, or 100% slower, who cares? It's not. If you can see, you don't see the interpreter in the profiler in an optimized program. So what's the point of doing all this in assembler, right? Here we have, like, on average, say 5,000 lines of C for each platform. So we got maybe like assembler. We got maybe something like 35,000 lines of assembler code that we're maintaining. To what end? For me, it's historical reasons. For me, there's no value proposition in this for RaptorJIT. So What I want to do, and haven't done yet, is to rewrite all of this in C. To make it simpler, I want to take that 35,000 lines of assembler for 7 different architectures and turn it into 2,000 lines of C code, looking much more like the Pucklua from Brazil virtual machine. And the point of that is that the bytecode interpreter is not performance sensitive. It needs to be optimized for maintainability. When we identify some very important optimization that's going to have a huge benefit for applications, we need to not get blocked by problems and complications in the interpreter. We need to update the interpreter very quickly and then get on with what we actually care about, which is probably the JIT compiler and this kind of thing. So my glorious idea of the future is to get this rewritten in C. I'm hoping somebody else will have an interest in that as well, actually, because it's an interesting kind of a programming exercise. But anyway, I see this as a big thing for what I'm thinking of as kind of RaptorJIT 1.1. It will open the door to some new optimizations that I find very exciting. But at the same time, I don't want to block everything while I port the VM, because it might take a little while. So that's kind of brain dumping context on the different worldview, you might say, for the RaptorJIT versus LuaJIT approach to the bytecode interpreter. Now, one thing I just wanted to talk about very briefly. This is the optimization that I'm most excited about in RaptorJIT, and this is something that I don't feel I can implement until I've got a VM in C, because doing it on the assembler code is just a bit tricky. And I should also say, in RaptorJIT, one of the very first things I did is just delete every VM except for x86-64, because this is to make the code somewhat maintainable. So when we do the table sealing, jumping back, when we do the table sealing, we're actually only going to update one VM. We're only going to update the x86-64 VM, and we're only going to do it for the 64-bit heap. We're not going to do it for ARM. We're not going to do it for MIPS. We're not going to do it for 32-bit x86. Not because those platforms don't matter, but because they're not worth the effort given the resources that we have right now. We want to get this feature working. We want to get it working for server applications, and that is a space that's dominated by 64-bit x86 CPUs. And we do want to generalize this to other platforms, but we're going to do that once we've made the platform support easier. So after we have ported the VM to C, then we're going to start bringing in new platforms. And we're going to be selective then as well. I don't think we're ever going to support a 32-bit platform, but it would be great to support ARM, for example, and it would be great to support, like RISC-V, these kind of things. So that's something that we want to do later. What we just don't want to do now is get bogged down in updating these 7 different VM assembler codes. 1 is already a pain in the ass from my perspective, so 7 would be. It's not my cup of tea, right? I'm sure some people can think of nothing more fun. Anyway, this new optimization that I'm very, 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 very excited about is called the 96-bit VM. Let me see if I can very briefly explain what that's about. Let's just do this with pseudocode. So if we pull up, so the idea here is to expand the native word size of the virtual machine from 64 bits to 96 bits, say. So what that means is in Lua, we pop back to our editor, we have this thing called a tagged value. This is something that's stored in memory, which contains both type information and a value. It's a tagged value, so it records what its type is and also what its value is. So, for example, if it's a Lua table, then the type will be a few bits saying that it's a table to identify it, and then once we've seen that, we know how to interpret the rest of those 64 bits as being a pointer. So we don't have all the 64 bits available for the pointer, but that doesn't matter because CPUs, they don't use the whole 64-bit address space these days anyway. So every Lua value is stored in memory as a 64-bit quantity, and that may have a pointer to an arbitrary amount of memory somewhere else on the heap. This is boxing, where you have this box that points to where the real object is. It's kind of just gives you the type information and then a pointer. And the big problem I have, the biggest problem I have, perhaps one of the big ones with the programming model, is that some values that we want to have a lot of and we want to churn through a lot, they can't fit into 64 bits on the heap, because the value itself is 64 bits and there's no room to add the type information. So anytime a value like this needs to be stored in the heap, it makes us go off and allocate separate memory and run the garbage collector and that kind of thing. And what I'm really talking about here is is like pointers and 64-bit integers. So if I would have some code like local counter equals 0, and I say that this is an unsigned 64-bit number, and then I want to say counter equals counter plus 1. So this line of code we have here, it looks kind of innocent, right? We've started with 0, 64-bit 0, and we've got a loop here that's incrementing that counter. So what is this? Is this one instruction, or is it more instructions? And the thing is that this depends critically on which optimizations manage to apply. So we have these two optimizations called loop optimization and allocation syncing, and they have this bittersweet quality where when they work, they're awesome. They can compile code like this down into just one instruction to just increment something in a register. It's fantastic. But those optimizations are not always available. It's very difficult to understand when you can count on them. It's intractable to explain that briefly to an application programmer when they can depend on this kicking in. And when those optimizations don't kick in, then this is a big deal. This is if you think about, if this value actually has to get stored in memory rather than in registers, then saying counter plus 1 is going to go out and do a malloc to get some memory to represent a 64-bit number, and then it's going to store a tagged pointer to that memory. So every single time in principle, if you think about just the semantics of the language, if you discount optimizations that are not completely dependable, then every time you increment a 64-bit number, you're doing a heap allocation, you're doing a malloc, you're running the garbage collector, all this kind of thing. So that's some nasty stuff. And I see this all the time in practice, that it's very tempting to just use these, and the same, by the way, is true of pointers. So if we would also say local array is an array of we're going to say we define some struct. So suppose we have an array of structs, and we would want to say local x equals array, something like this. Then when we assign x to one of these array elements, this is going to be a pointer to a struct in the C heap, and that pointer is also going to have to be allocated on the heap, because that's just how it works. You can't fit a pointer to a foreign function, to a foreign FFI pointer. You can't fit that into 64 bits, because you need to have the address, which takes up most of the bits, and then you also need to have the type. And in LuaJIT VM, you have enough type information to be able to say that this is a pointer, an FFI pointer, but you don't have enough space to say to what type. So you need to do this separate malloc somewhere where you have the actual type, the C type as it's called, saying that this is a struct with int xyz, and also where in memory that actual value is. So you kind of end up with you get a lot of indirection. And again, every time you do an array access here, in principle, if you don't count on optimizations that aren't always there, if you think about the worst case scenario, if you be conservative, which is you'd be prudent, then you have to look at this and say that's every array access here is a heap allocation, and every increment, any arithmetic on an array, on a pointer or on a 64-bit value is a heap allocation, and this is a big deal. So if you put heap allocations in the loop, you lose a lot of performance. You also get exposed to a lot of latency problems because you're running the garbage collector, and the garbage collector is very good. It's very incremental and everything, but it's not as good as just not allocating, for simple things like arithmetic. It's not cool. And the reason that you kind of get away with this for so long, so actually most of the time you can kind of write code like this and trust the compiler that it's going to optimize that away. So in Snab we write code like this all the time, and most of the time it works, but much too often it blows up in our face, and sometimes it takes quite a bit of testing to find the bad cases where it blows up. And so the reason that it works as well as it does is that the compiler is very good at not writing temporary values to memory, at keeping them in registers. And the interesting thing about the JIT compiler is that when a value is stored in a register, it's statically typed. So the value in if you store a pointer to a struct in a register, this is in register RAX, then the compiler knows what the type is. It's statically typed machine code, so to speak. The intermediate representation is statically typed, so it doesn't have to put the type tag anywhere. The type tag is implied in the intermediate representation that was used to generate the code. So when you're in the JIT domain, when you're operating on all these values in code that has been just-in-time compiled, you don't have to do any of the allocations. You just put the value in a register. You know already that it's an array or that it's a 64-bit integer, and that's enough. You don't need to record that anywhere because you know. The only times you need to actually do the allocation is when these values escape from a region of JIT code, and even transitioning like from root traces to side traces, that's okay. Actually, so even when you have these very branchy loops that go around a lot, that's okay. The compiler does a very good job of detecting when a value does not really need to be allocated. So 90% of the time, it's got your back, 95% maybe. But that 5 or 10%, that hurts. Then that's when you're losing a factor of 2, a factor of 10, or something in performance, or something that might surprise you. And that just a moment, please. Pardon me, I had to supply some Lego to my co-working friends. Anyway, code like this most of the time compiles very, very well. The just-in-time compiler will see this code. It will see what the types are when it's recording. It will know that X is going to be a pointer to a struct of XYZ. It will know the counter will be a 64-bit value. It will encode that type information into the intermediate representation, and it will never store that anywhere. And you won't have to do any of this boxing because 64 bits is enough to store the value in a register. You don't need to store the type information anywhere, and things are great. But anytime that a value escapes from the JIT and needs to go into memory, then you do take the allocation hit, and it does need to get boxed. So the simplest way that this happens is if you just a second. It wasn't all needed. I got a refund, a partial refund on my Lego. So when the JIT sees code like this, it compiles it very well. But when a value escapes from the JIT, then you get a heap allocation. The easiest way a value escapes is if you store it in memory somewhere. You have a table, a Lua table somewhere in memory, and you say, if we would say, like we have this local, or t is a table, and if we would say t.x is x, then we are basically saying we want to take this value that we have in a register and we want to write it into the heap. So then you need to put it into a representation that is valid on the heap. That means you need to put the type information as a tag. That means you need to box it. And the other way that happens is just with the way that traces are connected. Very often you have a hard time guessing actually where traces of machine code start and end, and it can absolutely be that when you do a loop, you have two separate traces of machine code that need to pass values to each other, and this happens via the Lua stack, and values on the Lua stack have to be tagged. So you can also, even if you're not storing it in a table, even if you do have code like this, just depending on the way your loops are structured and the way the scope of your variables is declared, it is entirely possible that, and you know, not unusual, that a local variable actually needs to be committed to the Lua stack in memory, and that incurs a heap allocation. So this is a good and bad situation, right? 90% of the time the JIT avoids all the allocations and life is good, but the other 5–10% of the time the values do go into memory, and the problem is that that just destroys your performance. You know, now your arithmetic has gone from being one instruction to being a malloc and an incremental run of the GC and all of this stuff. You don't want that. So what I want to do, a big thing with RaptorJIT is I want to focus on the bad cases. I want to say that the good cases are already very, very good, no problem. The problem is that the bad cases are very bad, and we can't be certain that they never happen. In practice, they can happen, and the conservative and prudent thing is to assume that they will happen. So then we've got to optimize them so that the gap is not so big. That's a huge thing with RaptorJIT for me. Make performance robust and predictable by having more redundancy in the optimizations. Never put all of our eggs in the allocation syncing basket, because maybe allocation syncing won't apply. Likewise, loop optimization. So my thought is to make the word size on the VM bigger. So whereas today we have 64 bits, when we store something in memory, it's got to fit into 64 bits. So we can get a little bit of type information, and we can get a reasonably satisfying amount of data. But we can't do, for example, a 64-bit integer, because we need all 64 bits for the value. We don't have any bits left over to do a type tag. So if we reserve some bits for type tag, then we can't fit a 64-bit integer, which means it needs to get allocated separately, which gives us the whole, you know, heap allocation thing. I think the simplest solution to this is just to make the tag values in memory bigger. I'm proposing 96 bits, which may be more than we need. But so then the idea then is, in memory, we would have a tag for, suppose today we have, I don't remember the details, but suppose we have a tag that is like 4 bits, and then we have a value that is 60 bits, something like that. So the situation today is something like that, where we have a tag that's enough to say, like, this is a pointer, not enough to say what kind of pointer it is. We can at least say that it's a pointer, and we have a value which for some things will be fine. Like if this is a pointer to a Lua object, 60 bits is enough, or generally with pointers 60 bits is enough to give the address, because it's just the reality of CPU architecture that we don't use all 64 bits at the moment for the foreseeable future. And the problem case is just if the value is 64 bits, then you can't fit it. So what I propose to do is to say that the tag can be 16 bits, 32 bits, and the value can be 64 bits. This is my thought, and maybe 32 bits may be too much for the tag. It might be okay with 16 bits or something, but anyway, that's my idea. So if we would luxuriate like this, then what we're saying is that we have, even when we're storing things on the stack, even when we're storing things in tables, we always have the full 64 bits available for storing our value, and we can still store the type. And actually we have so many bits for the type that we can store the full type there. So if a cell in a Lua table would be 96 bits, and we wanted to represent, for example, this X here, which is a pointer to a C struct with int XYZ members, then we could do that. 32 bits would be enough to say both that this is a pointer to a foreign object, and to give the C-type ID of that foreign object to say it's a pointer to a foreign object, which is a struct of 3 integers, XYZ. So we don't need to store type information off on the heap anywhere. And similarly with the value, 64 bits is enough to encode both FFI pointers and also 64-bit integers. So if we would do things, if we would have this scheme, then it would never, ever, ever be necessary to heap allocate pointers or 64-bit integers. When you would write code like this, that's doing pointer arithmetic, that's doing 64-bit arithmetic, that's loading, dereferencing FFI pointers, there is no possibility for this to incur a heap allocation, because semantically it just, there's nothing here that requires a heap allocation. Everything fits in a 96-bit tagged value. So we can write it on the Lua stack, we can write it into a table, that kind of thing. So then we still have a situation that the JIT compiler will only, say, 95% of the time succeed in keeping things in registers. But in the cases where things spill out from registers onto the stack or onto the heap, we're probably not going to notice the difference that much. It's going to be a little bit slower, but not like a factor of 10 or 100. It's going to just be a little bit slower, and I think that's okay. If the worst case and the best case are pretty close, and we have significant programs that sometimes get a mix of the best and the worst, I think it's all going to come out in the wash. And from a user perspective, you're always going to get the performance that you expect. You'll never get a bad case that's so strong that it changes the whole character of your application, which is the problem I have with LuaJIT today. So that's the 96-bit tables idea. I'm very excited about that. I want to implement that, but I've looked a little bit at the assembler code for the virtual machine, and I just think it's too much work to make such a fundamental change as changing the word size of the VM. I don't want to do that in assembler. I'd rather do that in C. So what I want to do is first get the VM rewritten in C, and then do this and see if this is as wonderful and promising as I think it is. That's that topic. So coming back, I'm glad I wrote down our stack. Coming back to what we were doing, we've now talked about the continuous integration where we bootstrap the VM. We've also talked about the character of the VM written in assembler, and the idea for a 96-bit VM, and maybe an 80-bit VM would be just as good. I don't know how many type bits we need, but anyway, it's all much the same. What we'll do now is, I think, have a 5-minute break to refill coffee, and then finally end our digression, come back to what we really kind of want to do today, which is to survey the code that we're going to have to hack to make our sealed tables really work, to get the right semantics so that we have this barrier on table writes. And this is going to involve looking in both the JIT compiler and the assembler code for the VM, and we get a feel also for whether we're willing. Is it only a small change to the assembler code that we're willing to do, or is it, if it turns out to be much more involved, we can think about whether we want to defer this, like the 96-bit VM idea, to a RaptorJIT 1.1, where we've also got a VM written in C to just reduce the cost of implementing this optimization. I am hoping that this one will be simple enough that we just hack the assembler code, but we'll see about that in 5 minutes, let's say. Back soon. Oops, back we come in total darkness. So we had just done a whole morning worth of digression, and now we're coming back into looking at the code to try and look at how the last bit of our sealed table optimization, the barrier on writes, can be implemented. So what we're going to do now is just do a dive into the code and just try and get our heads around that. What is the code that we need to touch? How does it look? Does it look realistic? Is there any existing things we can piggyback on? So there's actually a couple of on the topic of piggybacking. There are already some similar things that exist, and it would be very convenient if what we need to do is well aligned. So what we want to do is every time the value of a table changes, so when we do an update to a Lua table and we change the value of an existing entry, we want to execute our barrier. We want to do a check to see if the table was declared as sealed, and if it was declared as sealed, then we want to invalidate the machine code so that everything runs again. That's what we want to do here. And there are some other kinds of barriers on tables already. One is with the garbage collector. The VM has an incremental garbage collector, and it's always keeping track. It does this coloring of objects. It has certain invariants about what colored objects can point to what other colored objects that need to also be maintained when you do updates to the heap. So the garbage collector already needs some work to be done when you update a table on the heap to defend its own invariants. So it would be very convenient if the invariant that we need for table sealing is sufficiently closely aligned with the invariant that the garbage collector is already implementing. So we'll just see when we go through the code. Hopefully, when we find the relevant bit of source, we'll see what the GC is doing, and we'll see how well that suits us and whether it can save us some work. And there are also some other kind of barriers in the JIT, in the intermediate representation. There is a table write barrier that might also be relevant. We might need to do something in the JIT in order to optimize these updates. You know, if we have a loop that's updating a table over and over again, it might be sufficient to just check once whether the table is sealed and not have to do it all the time, that kind of thing. So on the JIT level, I mean, we're especially concerned about performance at the JIT level, right? So we've already said the interpreter is generally not running at all in performance-sensitive code. So a change, a little bit of overhead in the interpreter is not going to be measurable, detectable. I don't expect. But in the JIT, it could be substantial. It could be dramatic. So we need to actually make sure that we get good code for the JIT, and it's very nice then that there are already some table write barrier concepts in the intermediate representation, and we can potentially tie in with those or do something very similar to those for the sealed tables, so that we get good code and we get efficient kind of maintenance of our invariant. And the whole feature depends on this, right? So if it turns out that the performance we gain from sealed tables is then lost in kind of defending the invariant that it depends on, then we got to throw the whole feature on the scrap heap. We will have learned a lot in the process, but so it's important. So what we're doing is performance sensitive, and the whole concept depends on this. So in a sense, we were oversimplifying doing our MD5 benchmark because we were not seeing any potential cost of defending the invariant. So it's entirely possible that the whole idea sucks. So it would be interesting to dig a bit closer and see. Let's do that. Should we start with the JIT compiler or with the bytecode interpreter? Let's start with the bytecode interpreter, just for fun. So that, and we've already said if we're in the LuaJIT source tree, we have 7 different bytecode interpreters all written in assembly language. We're going to concern ourselves with the x64 one. So now we can pull up the bytecodes that we're interested in. Table ops. So these are the bytecodes that the VM understands for operating on tables. So we have some table set bytecodes. And so presumably what we want to do is find the implementation of these table set bytecodes and add, see what invariant checks are already happening in there, and then figure out how to fit ours in. So let's just do that. We'll just search the code for t set and see what we find. the set. There is a bytecode definition of table set value, t set v. So what do we got? First, so let's just go down a little bit here. It starts to become actually, well, I'm just gonna extract out the code for this one bytecode to start with, so that we can focus on that. I had a quick peek earlier, and I think actually it's a bit of a copy paste here. It was my impression that the implementation of these bytecodes is very similar. We get this like a couple of pages of assembler code, and it's similar but not identical for a lot of them. I'm not sure about that, and it's tricky with the assembler code, right? There's a lot of go-to branches in here and stuff. So in a perfect world, we would have already ported the VM to C. We would not be reading assembler code here because, again, we just don't care enough about the interpreter performance. You know, like a very fast interpreter is as slow as crap, and so we just wish this was already written in C, but it's not. So we're just going to do this. Okay, I'm going to copy paste into a separate buffer that code just so that we can hop around more easily. So let's read this and get a feel for what it's doing. And I took this from LuaJIT, and LuaJIT has a lot of build time conditional features. So there are a lot of different kind of heap layouts, different features in LuaJIT, and you can pick which ones you want at compile time, and then they're if-deffed in the source code. So one of them is this dual number thing, where you can represent numbers either as kind of floats or as integers. You can kind of, in more of the intermediate representation, you can, you know, to be honest, I've never fully understood how this dual number feature works. I've tried doing A/B testing on it, and I've never detected any meaningful difference on x86. And I've talked with other people who have done the same thing and also could never find any difference. So I've always found it a bit confusing, and I've never dug in too deep. And on RaptorJIT, I just removed this because this is something that kind of permeates through the whole VM definition, having multiple schemes for how you encode simple things like numbers. So for me, maybe we should even look at this on the RaptorJIT source tree. I think we'll do that because I've been going through and looking at these if-defs and deciding once and for all whether that feature is in or out. And often, in the case of this feature, at least, it was out, you know, and like with the 64-bit heap, that was in, and then there was no such thing as the 32-bit heap anymore, and that kind of thing. So I've tried to resolve these, like, not at compile time, but at at check-in to source control times. I've deleted a lot of code, so we're going to actually hop out of LuaJIT at this point. So we were in RaptorJIT, no? I know we're in there. We're gonna hop over to RaptorJIT anyway, just because I've stripped the code down quite a bit, removing code that I don't care about. So let's do that again. Let's find t set v here, and we'll do the same exercise of just extracting that code. And I don't want to be rude about this, right? Like, LuaJIT is an amazing piece of engineering, and Mike Paul is, you know, 100 times the programmer that I will ever be, and I don't want to detract from this. And what works for Zeus, who may be able to maintain, you know, 7 different assembler architecture ports, or juggle them all in the head at the same time, that doesn't necessarily work for mortals. So something that is a good idea if you're a genius is not necessarily a good idea if, like me, you're not a genius. So that's the reason that I'm assessing things in a very different way. I look at this from my own perspective. I say, hey, I'm maintaining this project, right? This is forked. I gotta worry about this for myself. What is the right trade-off between complexity and cleverness and maintainability? And for me, it's just it just looks very different than for the way things are done in LuaJIT. A lot of stuff in LuaJIT is just done much more cleverly and kind of, from my perspective, complicatedly than what seems justified to me, because it's not my thing. You know, some of these things are not my thing. I'm an applications person. I want to get the compiler doing what I need for my application, and then get back to my application. That's my perspective. Anyway, stop blathering. Let's have a look at this code. So the main loop, when it gets a t set v instruction, I'm going to start doing this line for line, and we'll just see whether that makes sense and whether we should skip around a bit. The first thing it does is this run this macro ins abc. So this is decoding the parameters out of the instruction. You know, there are a few different formats that a bytecode instruction can be in. We might have that. Yeah, so you always have your operand or opcode saying what the instruction is, and then you can either have parameters A, B, C that are all quite small, or you can have parameter A and parameter D, which is extra big. So if you have a D, then you can't have a B. If I'm remembering this correctly. So that's the thing. You always have your opcode, you always have your parameter A, and then you either have a small B and C operands, or you have a combined D operand, and which one you get depends on what we see. I mean, this is the kind of definition we're looking at here. So it depends on what makes sense for that bytecode. So if you need a literal value, then you want the space for both, I guess. So you do it like that. Oh no, okay, there's literal there as well. Anyway, some different instructions have different needs, different numbers of operands, different kind of sizes of operands, and in the bytecode instruction set is kind of defined here, how that is on an instruction by instruction basis, and then in the code you have this little macro that then just pulls it populates the CPU registers with the appropriate operands from the instruction based on what that instruction's operands are. So it's saying here that this instruction, the tsetv instruction, is an ABC instruction. So it has the A and the small B and C operands, and no D operand. That's what that line there does. Then, so this assembler is dinasm. So it has some basic understanding of C types. So we have a type. I'll hop back into the main source file actually to just illustrate this. We're doing an x86 move instruction. The destination register is RB. Okay, let's make this concrete. We'll hop into the, because there's some declarations this is referring to. So first of all, the destination register is RB. So what's RB? That's not the name of a register on x86. So we search for RB. We see that is the x86 register RBP, and we see in a comment here that register has been chosen with the awareness that it is call-e save. So that means that we are allowed to trash the value of RBP at any time without having to save it on the stack, because the platform ABI says that if anybody has called our code and they cared about the value of RBP, then call-e save. Anyway, I don't care. Let's let's take this. Let's just get through this. We are loading into the register RB, which on our platform is RBP. So RB is like the abstract name of the register in the VM. It's the register that holds the B. It's the register that holds this B operand from the bytecode. That's what the B means. It's the register for the B value. We're loading that. This register is statically allocated kind of for the whole VM. Anytime you store the B operand, it goes into the CPU register RBP. So it's like a static, global register allocation. But it's tricky, right? This is an assembler program, so it doesn't mean that at all times you have this RB. It's just kind of, well, it's the programmer's responsibility to make sure that this is true at the times when it needs to be true. And they're allowed to break that at the times it doesn't, and everything. That's assembler programming. And we're also saying, okay, we're saying we're loading the B, and we're saying that it's a table, I think is what tab means. So let's search for tab here. Yeah, so it's saying that when we say that something is a tab, when we say that a register is a tab, this refers to a C structure type called GC tab, which is the heap representation of a Lua table. So this is like some static C-type declaration being done on the assembler code, saying that we're loading the register RB with a value that is a table. It doesn't have to be, right? We're saying that this time it is a table, and this at this point, this is just a comment essentially at this point. And then, okay, where are we getting it from? We're getting it from the base. So the base is a pointer, is the address of. It's like, you know, in the VM you have a stack, the Lua stack. Lua is a stack-oriented language, and you can push stuff onto the stack, but also like a part of the stack is really used more for local variables and stuff, more like a traditional stack frame, more like for indexing with registers, where you say, well, this region of the stack here, this is where I'm putting my temporary values, and you know, I'm going to have 7 of those. So I'm going to reserve seven stack slots for reading and writing, but you know, in an indexed way for dealing with my local variables. So the local variables go on the stack, as I understand it. And so base is like the where our local variables are, you could say. So we're relative to the base. We're then adding. We're adding the RB. Okay, so we decoded the instruction, and we put the B operand in the register RB, and now we are replacing. We're replacing the value in RB with. So we're in RB from the instruction, we got an index where you can find a table, and what we're doing here is dereferencing that index to get the actual table. So base is a pointer, you know, it's an address on the Lua stack where we're going to find these tagged values. These are the things that are currently 64 bits, and we're talking about expanding to 96 bits. This is an index into that stack containing these 64-bit tagged values. That's the address it starts from. It's adding to that RB, which is the what we found in the bytecode, times 8. And this times 8, that is exactly the 64-bit thing. So if we want to make the VM operate, I'm digressing slightly again. If we want to make the VM operate on 96-bit values, then one of the things we need to do is change all of these times 8s into times 12s. And that's actually interesting. I'm going to digress for only a short time on this, but it's actually quite interesting when you think about this on the assembler level. I want the C compiler to deal with all of this, but on the assembler level, you can say times 8 here. You can't say times 12 there, because this is just, I mean, this is not a multiplication instruction, right? This is a move instruction. This is an address in assembler, and the addressing support on the CPU lets you do a bit of arithmetic. You can take a base register and add another offset register and multiply that offset by 1, 2, 4, 8, or 16, if I'm remembering correctly. Maybe slightly more, but anyway, you have a small number of power of 2 multipliers that you can apply for free, and you can also add a constant afterwards. So here it's using these x86 index loads to get, you know, for free the array index. But we wouldn't necessarily be able to do that. We couldn't put a 12 there. So this is something we'll need to think about and deal with in doing the 96-bit VM. And again, this code is not performance sensitive. It's a historical accident, as far as I'm concerned, that this code is written in assembler. This code shouldn't be written in assembler. It's not performance sensitive. So this kind of very, very careful, you know, instruction set oriented optimization doesn't make sense. For me, from my perspective, in RaptorJIT. In LuaJIT, totally different. I would get shouted, thrown off the building or something if I said that and called an idiot and all the rest of it. Whatever. That's what I think. And another one here, we have this. We have a shift left. No, sorry, that's a shift left. There are also a lot of shift rights around, where we do like often we also need to do a kind of a pointer difference, where we want to see how many words we want to compare two pointers and say how many words are they spaced apart. And to do that, we need to subtract them and then divide them by the word size. And division by 12, that's actually potentially very expensive. So integer division is actually very expensive, even on the CPUs of today. Whereas with a 64-bit word, division by 8 is cheap. It's a bit shift, right? So it's another thing that we need to think about. And again, a C compiler will have tricks for division by constant. I don't have it in my head. The hacker's delight trick for dividing by 12, whether that's has any significant overhead and everything. So again, it's actually stuff that it's stuff that we're going to have to worry about. And again, I don't care so much about here down in the interpreter, but anytime these things bubble up to the JIT compiler, then it's actually significant, and it could potentially be an issue. Anyway, so I guess this is being a useful vehicle for brain dumping about a lot of things, even if we're getting very slowly. We're only kind of 2 instructions into this thing. So I mean, I'd actually like to go a bit quicker here. Let's not spend all day just going through this. So let's just go through quite roughly. We want to see if there is any code that's already similar to what we're doing in here. So we want to. This is a table set. We want to say if this is changing the value of an existing entry, then we want to check an invariant. We want to see if the table is sealed, and if so, we want to branch out to an invalidation routine. So let's just scan down and see if there's anything like that. And we can see this. We can see some of this GC stuff going on. So there's a reasonable chance that there's something reasonably aligned. What do we got? We load the table off the stack into a register. We load RC as well. So what was that? That was possibly the value that we want to store, or the key, or something. Where do we have it? T set v. So this is the bytecode we're looking at. It's where B is going to be the table, and C is going to be the index, the key, and A is going to be the value. So here we're loading the key. The table we want to store into is in RB. The key, which can be any object, is in register C. Now we do check tab. So what is the check tab macro? Check tab does check that something is a tagged pointer of type tab. So this is looking at inspecting the tag bits on this 64-bit value to check if it's a pointer. And then there's a target. So I guess that's the target must be where we go if it is not true. Check TP takes a register, a tag pointer, a tag, and a target. It loads the type register. So again, there's a register called iType. Let's be concrete. The x86 register R11 is by convention the register where we store internal types of Lua values, the type tags, and it's significant. Here we have a routine that is dealing with RB and RC, and here via a macro with iType. So of course, with our kind of static register allocation thing, it's very important that these don't get mapped onto the same registers. That RB and RC and iType are not all allocated to the same register. That would be a problem here. Then they would be overriding each other. And this is assembler code, so we are responsible for that. Anyway, yes, and then it loads the type, masks off the value bits, so you just have the type, and it compares the type with what we expect. And if it does not match, then it branches away. So what this line is saying is, if the value that we loaded in RB is not a table, sorry to hop back here, but this is our bytecode. So if we get a B here that we're indexing that is not a table, then we should branch to v meta t set v. So if you try and index, do a table index on something that's not a table, that can be okay if it is an object that has a, Lua has these meta methods that has operator overloading, and one of the kind of operators is table indexing. So it can be an object, it can be a foreign function object, even it can be a lot of different things other than a table. And what that's just saying is that at runtime, if the value here is not actually a table, then we go somewhere else. We go to this other. This is just a go to another bit of code called vmeta set v. So we if it's not a table, then we've got to branch off somewhere else and deal with the case that we're storing via a meta method on something that's not a table. Whereas if we continue down here, then this is the code dealing with storing into something that actually is a table. So this is when it's a table in RB. Table could still have a meta table too, but let's not get ahead of ourselves. And I guess it would be easy to complain at Lua like this. I could say, well, why do we need such funky semantics? Can't we all just pretend it's like a Viet language or something? But anyway, I think Lua has quite clean semantics, right? So this meta tables and stuff, it does require quite a bit more code. But I think if you would compare this to JavaScript or something, you would just count your blessings and everything. So it doesn't bother me that there's a bit of complexity from this stuff. Again, I'm like a list packer really by background. So for me, it all seems a bit kind of like within a reasonable comfort zone of kind of language complexity. I quite like Lua. It's a neat little language that just, it's a small dynamic language that doesn't suck, right? There's a lot to be said for that. Okay, so is the key an integer? So this is interesting. I think this comment is referring to code that doesn't exist. I think I maybe did a sloppy job when I removed this dual number mode. We compare this with LuaJIT code. Yeah, so they had this if def here where they check whether okay, so then we see what the dual number is about. That's about being able to store values on the heap and declare that value is an integer rather than like a float. So in LuaJIT, at build time, you can decide whether you want the VM to have the concept of an integer stored on the heap or on the stack, whether a Lua value in memory can be an integer as distinct from a floating point number. And that's a build time option. I've never seen it actually have any value, including in integer heavy inner loops, many of them. I've never seen any value in that, so I just removed that. But obviously I didn't remove the comment entirely, so I don't think we want that. That's this comment and this comment. But we'll take that out while we're there. Well, it's only a scratch buffer, but anyway. Again, not trying to take all day here. Check if it's a number. And we've already seen when we do this check, the branch target we give is if the check doesn't succeed. So we're checking if this is we're checking if RC, which is the table key, is a number. Again, this is our bytecode. B is the table, C is the key. So we're checking if the key is an integer. And again, we get to the Lua. Okay, this is coming back to Lua semantics, right? The reason we care whether, as a special case, whether the key is a number is because Lua represents tables in a kind of a dual way. You actually have an array in memory part that is, if you're storing things that are indexed like 1, 2, 3, 4, 5, those actually go into a dense array in memory, and it also has a hash part. So if you store something else like like a Lua object or random numbers or anything else, then that goes over there. So when you update tables and look into tables, you need to figure out where you're going to look. Are you looking in the array part or the hash part, or all of this stuff? So that's why we're here checking if the key is a number. If it is not a number, then we're branching to label 5, which is down here. So presumably this code here is concerned with numeric keys. So when we have potentially something stored in the array part of a table. Okay, so a number in Lua is a floating point number. So if we want to use that as an index, then we load it into a floating point register. We do a conversion. we load it into a floating point register. We do a convert from floating point to integer to get it back into RC, and we've got it as a 32-bit number here actually. RCD. We had RC declared. So RC is RAX, and RCD is EAX, which is the low 32 bits of RAX. So if we say RCD, what we mean is a double word part, 32-bit part of RC. Then if I'm interpreting this correctly, we then load it into another floating point register, see if they agree, which I guess is checking whether we lost anything when we truncated this to 32 bits. So I guess that this is an overflow check on whether it was a greater than 32-bit number that I guess would not be eligible for well, actually maybe it's more generally checking if it's an integer. We knew it was a number, but now we know it's a 32-bit integer. So it might have been fractional or something, which wouldn't work as an array index. Okay, fine. And again, if that doesn't hold, then we branch somewhere else that deals with the more exotic, like metatable cases and everything. So let's assume we get through all of that stuff and get down to something a bit more meaty. So what do we have here now? This is something where we're looking at an invariant for the garbage collector. So sorry to bore you with this minutia and me again familiarizing myself more with this code because again I spent a little bit of time familiarizing myself with the assembler code. I reached the conclusion that I wasn't interested in this code and I wanted to replace it, but I haven't done that. So I'm not expert on this code, and I never kind of plan to be. I'm just kind of going along, figuring out as much as I need to as we go in the short intermediate term. Anyway, we get through all that. We've loaded the array part. We've made it all the way down here. Finally, we're doing something for the garbage collector. What are we doing? We test whether the tables, so this is interesting. We're looking at a flag on the table, whether it is marked as black. So I'm just thinking aloud here. It's potentially what we want to do here, potentially, is something like sealed, and with, potentially. So there's a special case here that if the table is marked as black by the garbage collector, then we're branching out to label 7, which is going to do something special. So potentially we could do something very similar here, and let's say we would jump to label 99, which would have our special case code for stores into sealed tables. That would be where we say that we've broken the seal, we've violated the invariant that table sealing depends on by making the table contents in memory newer than the table contents in machine code, and then this is where we would invalidate the machine code. That would be kind of exciting. Okay, so let's see how this works with the GC first to see. I mean, we're gonna have to really look very carefully at all this to make sure that it's tricky code with lots of branches and everything, right? So we're gonna have to do a few iterations to really know which way is up and exactly where we need to hook in our invalidation of the machine code. Where do we actually store a tagged value in a table? We might be even able to work backwards from that, find the instructions that are actually taking a tagged value from the stack or from somewhere and poking them into a table, and just make sure that all those are covered. But anyway, we just keep putzing along as we do right now. So down to label 7, that is what the garbage collector does. It will do this. It branches. If the table is marked as black, it will branch down here. It will execute this barrier back macro, and then it will branch back here. So what does barrier back do? Is that in any way related to what we want to do? Move table right barrier back overrides the register argument. So we mask. Now we're actually not looking at our problem, right? We're just trying to get a little bit of an understanding of what the GC is doing here, because then we're going to have to go, we'll get a little bit of a feeling for what the GC is doing here, and then later we'll go and have a look at exactly what invariants the GC has and how closely those relate to table sealing, and whether this does provide a kind of a paradigm for how we can maintain our invariant. But just briefly, to just get a feel for what's happening here. The table has a value called marked. We're masking that to convert from black to gray. Okay, we're making it. We're updating the mark on the table from black to gray, says the comment. We are loading a global variable for the VM called gray again here. We're then taking our table and storing that in gray again. Okay, so we change the mark on our table. We are loading the existing value of a variable called gray again into a scratch register that was provided. We're then replacing. We're doing a swap here. Then we take our updated table and we store that as being the value of the global variable gray again, and then we take the old value of that and set that as the GC list. So I don't have it in my head this is establishing some kind of an invariant for the incremental GC, so that it knows which objects are next to scan and which ones have already been scanned. It's going to be very interesting I think to actually have a look at what the GC's invariants are and think about how closely those relate to what we want to do, and then I guess I would normally do this in a few iterations. So ultimately, the code change that we're going to need to do, ultimately, we can kind of figure out the shape of it, right? So we have all of this assembler code, and we just looked at one of the table setting bytecodes. I think there's several that all have similar implementations. What we need to basically do, when we finish this, when we thought everything through, what we're going to have is a diff where every time there is an instruction that stores a new value into a table cell, not as a metatable thing, but as an actual value going into a table, that when we trace backwards, that every execution that leads to that instruction that updates a table has checked our invariant of whether the table is sealed, and if so, to invalidate the machine code. So that's what we need to do. And we got a few approaches, and I would tend to look at it from a few different angles to try and get my head around it. And I still am kind of not committed to doing this change on the assembler code. It might be better to push this to RaptorJIT 1.1 when we have a CVM. But we look at it from a couple of angles. One is to look at the existing invariants for the garbage collector, see whether logically those are very well aligned with the table sealing, in which case we can kind of, potentially we could even add our stuff in here. If it turned out that we needed to update the table sealing invariant at exactly the same time as we need to update the GC invariant, then maybe we could just update this macro and be done with it, and it would automatically put the code in all the right places. If it's not quite so well aligned, then we'll need to just to think a little bit harder, and we're going to need to identify all of the instructions in here that do store a value in a table and make sure that those can only be reached by paths of control that also check our invariant. I think I'm satisfied for this session right now. Thank you for tuning in. I hope that these digressions and brain dumps have had some some value. I got a really nice comment on the weekend. Somebody said they were enjoying the videos. That's lovely, because I just started doing this. I never really known about the live coding concept. So I was thank you John Wayne, which may very well be a pseudonym. Thank you very much. It warms my heart to get some nice feedback, because this is of course an experimental way to kind of share a little bit, spread a little bit of information about how this software works. To both to make, for people who are just interested in that topic, and also so that anybody who actually wants to work on the project has a little bit more resources. If in the future someone is wondering what the hell I was thinking when I did a certain change, then, well, I'll just be able to say go to this page and you can find out. Anyway, enough of all that. Thank you very much. Catch you next time.